All right, AP Chem, here is a walkthrough for office hour questions for Friday, May 8th. Go ahead and go to the link in the document, go to question number 5, give yourself 9 minutes to answer it, and come back here for the answer. So if you get a question like this where they're graphing concentration, natural log of concentration, and 1 over concentration versus time, you're looking at a rate law problem. And it'd be a good idea to have a note guide handy for the actual AP test just to remind yourselves which one is which. But this would be a 0 order. If it was a straight line, this would be a first order if it was a straight line. And this would be a second order if it's a straight line. And that's what we have in this problem. We have a straight line for 1 over natural log, or 1 over concentration, so it's a second order. So that's your answer for A, second order, and that's it. For B, sorry. Just B. For A, for trial 1, calculate the initial pressure in the vessel. You need to go back to your trial 1, and you want to look at the first graph here for concentration. So for trial 1, where the open circles here, the initial concentration is right here, 0.020 moles per liter. And I need to use that molarity and the ideal gas law, PV equals nRT, to solve for that pressure. Now, how do I do that? I need to know everything else in the problem if I'm going to solve for pressure. So you're given temperature in the problem. R is a constant. What do I do with my moles and my volume? Well, there's 2 things you could do. You could assume a volume, so consider any volume you want to. 1 liter would be a great choice. And if you choose your 1 liter and then you use your molarity, you could calculate the number of moles and you'd have N and you can solve for P. But another way to do that is to rearrange this equation. And if you rearrange the equation, I'll show you their math for right here. We were given moles per liter at the initial, the start of the problem, 0.020 moles per liter. If you take moles and divide by your volume, N over V, you get moles per liter. So this number they gave you that we read from our graph at the very start right here, the initial concentration, is in our ideal gas law. We just have to rearrange our ideal gas law and divide by V. And if you divide by V, this right here is my concentration. And so you could take 0.020 moles and plug it in times R times your temperature, and you get this for your answer. Or if you assume a volume for your vessel, you'd still get this as your answer. So you get 1 point for a setup using ideal gas law and 1 point for your correct answer. For part B, you said second order. That's what you should say. And that's what we talked through with our shapes of our graphs. For part C, the initial rate of the reaction is given to you for trial 1. Calculate the rate constant. What you want to do here, you were given from part B this idea that it's a second order reaction, and that means you should be able to write this rate law. Rate equals K times my concentration of my reactant raised to the second power squared. That's what it means to be second order. So in this problem, they give you the rate. It's right here, the initial rate of the reaction. We want to calculate K. The only thing we need to know is what is this concentration. And that's the concentration at the start of that reaction. It gives us an initial rate. So we want the initial concentration. And that's what we used earlier in the problem, 0.020 moles per liter. And so I'm going to plug in 0.020 moles per liter for my rate. They rearrange the rate law. Solve for K, you'd get rate over your concentration squared, and this is what you should get for your answer. Now, make sure you pay attention to units in a problem like this. It's possible that you get points for your units, but in this case, you only get a point for the correct value for your answer. You could also do the second order rate law for this. I wouldn't prefer to use this method, but you could. This is on your AP equation sheet, and you can plug in your known values and solve for your K value there as well. So that's kind of a pain. I would do this first method. So for a 4-point problem, if you want to check your point values for that, let me jump to it. You would have 2.08 is your number of points. That was average. You can see how you did with that. I want to extend this problem, though, and let's go back and take a look at it. I just showed you the answer that what I want you to do, but try to draw the Lewis structure for C4H6. You can pause the video and do that. So it's good practice drawing your Lewis structures. If you're drawing a Lewis structure, try to make it symmetrical. And for symmetry here, this is what it would look like. You need double bonds to satisfy your octets of your central carbons. But after you draw a Lewis structure, I want you to consider what's happened for our rate of our chemical reaction here. For the chemical reaction, we start with this small compound with 4 carbons, and we turn into a compound with 8 carbons. It essentially doubles this molecule. So if you can picture this chemical reaction occurring, it'd be one of these molecules running into a second molecule, end to end, and it would break a bond and form a bond, and it would make one long chain. In other words, you need 2 molecules for that chemical reaction to occur. That's what this means when we say the rate law is second order. If you picture a a mechanism for this reaction where you have elementary steps for the reaction, that slow step is going to have both of these molecules running into each other. And that would be likely for this chemical reaction. It could be a one-step chemical reaction where both those molecules just run into each other. And that's what this second order is. It involves both those. We call those a bimolecular step. If you had three, a third order, you'd have a three molecule step in your chemical reaction. Okay, for your next problem, you want to go to number 6. You can pause the video and work through that. Give yourself 9 minutes for it, and I'll post a solution for that in a separate video.